Hi guys, so in this video, we will be mainly covering the resultant of forces, specifically the resultant of coplanar forces, which are could be parallel, concurrent, or non-concurrent. We'll also have some introductory topics such as your distributed loadings and moment of force. So let's begin. Alright, so what is mechanics? Well, this is a branch of the physical sciences that is concerned with the state of motion or rest of bodies that are subjected to the action of forces. Now, mechanics has three different branches: your rigid body mechanics, your deformable body mechanics, and then your fluid mechanics. For this playlist, we will be mainly covering your rigid body mechanics, namely your statics and your dynamics. Now, statics, it deals with the equilibrium of bodies, that is, those that are either at rest or move with a constant velocity. That means there is no acceleration. And then dynamics, it is concerned with the accelerated motion of bodies. And under dynamics, we have your kinematics, which treats only the geometric aspects of your motion, namely your displacement, your velocity, and then your acceleration. And then we have kinetics, that is the analysis of the forces causing motion. Alright, so for our first topic, we will be tackling statics. And under statics, the first thing that we're going to be discussing is force. So force is considered as a push or pull exerted by one body on another. In mechanics, this is any action that tends to maintain or alter the motion of a body or distorts the body, right? So the units of motion that we will, for the units of measure that we will be using for force, um, we have for SI, we have Newton or kilonewton. And then for English units, we will be using pound force. Now for the conversion of our units, so we have 1 Newton, that is equal to 1 kilogram meter per second squared, or 0.22481 pound force. And we have 1 pound force that is equal to 4.448 newtons. Alright? Now, all physical quantities in engineering mechanics are measured using either scalars or your vectors. Now, scalars are any positive or negative physical quantity that can be completely specified by its magnitude. Examples of this may include your length, your mass, your volume, your time, and so on and so forth. As long as you can express that quantity by just using the magnitude, we could consider that as your scalar. The next we have vectors. Vectors are any physical quantity that requires both the magnitude and a direction for its complete description. Examples of these that you will encounter in statics are going to be your force, position, and moments. Now we have something that is called your resultant vector, or just simply your resultant. This is the combination of two or more single vectors. Alright, so let's do a review of our force components. So let's say we're trying to solve for the first component of your force F right here. So what we're going to do is we're just going to project our force Fy, the y component of our force, and we're going to consider this right triangle. So if we want to solve for the x component of our force, we're just going to use cosine. So if you guys would remember your Soka. So if we use cosine, so cosine theta is equal to adjacent fx all over the hypotenuse f. And by that relationship, we have f of x is equal to f cosine theta. And the same thing for your fy. So we have negative f sine theta. So we have the negative here just to signify that our y component is acting downwards from the origin of our Cartesian plane or our xy axis. Right, so there's another way of solving this, which we will be mainly using when dealing with trusses or inclined members. So we have here a slope triangle. So this slope triangle is similar to this force triangle. So we're just going to be using your ratio and proportion. So your F sub y is proportional to your side B, and your F sub x is proportional to your side A, and your force F is proportional to your side C. Right? So we have here, if we want to compute for your F of x, so we have here, by principles of ratio and proportion, F of x is to F as A is to C. Now, by that mathematical relationship, we can solve for f of x. And the same thing for your f sub y. So f sub y is to f as b is to c. So by that relationship, we can now solve for your fy. And again, the negative sign here just denotes that our y component is acting downwards. So if you want some examples for solving force components, please watch the first video in this series. Okay, so for our main topic, we have resultant of forces, or just a combination of two or more forces. So under this topic, we will be mainly dealing with two types of them. The first one is the resultant of your coplanar forces, and then the second one is the resultant of your non-coplanar forces, or forces that does not exist in the same plane, or these are your forces in space. Now, under resultant of coplanar forces, that is forces that exist in the same plane, we will be dealing with parallel forces. And then we have your concurrent forces. These are your forces that are meeting at the same point. And then we have your non-concurrent forces. Same thing for your resultant of non-coplanar forces. We're just not going to consider your parallel forces in space. So we have for that one the concurrent and non-concurrent forces. Alright, so let's start with your resultant of your coplanar forces. So under that, we have our parallel forces. So let's first consider if our forces are acting on the same direction. So let's say we have here force P1 and force P2 acting on the same direction. So our force P1 is 40 newtons and force P2 is 60 newtons. Now to compute for the resultant of that, we're just going to add them. So P1 plus P2, the resultant would be equal to 100 newtons, right? So what if they are inclined and acting along the same direction? So for P1, we have 30 newtons. For P2, we have 50 newtons. And then for P3, we have 20 newtons. Again, we're just going to be adding them to get the resultant. So the resultant is equal to P1 plus P2 plus P3. That is equal to 100 newtons. What if they're not acting on the same direction, such as this one? Your P1 is acting towards the left, and it is equal to 40 newtons. And our P2 is acting towards the right side, and it is equal to 60 newtons. So if this is the case, we're just going to subtract. So since majority of the time, we consider acting towards the right side as the positive side, so we're just going to subtract P1 from P2, and that is equal to 20 newtons. But as a general rule, the direction of our resultant force is going to be the direction of the force that has a higher magnitude. Such as in this case, P2 has a higher magnitude compared to your P1. That's why the resultant force is acting towards the right side as well. Right? Another example, we have three forces right here acting upwards or downwards. So we have P1 that is equal to 60 newtons acting upwards. We have P2 that is equal to 20 newtons acting downwards. And then we have P3 that is 30 newtons acting downwards. So again, we're just going to subtract P2 and P3 from our P1. And that will be equal to 10 newtons. And since the force that has, or the direction that has the higher magnitude is acting upwards, our resultant will also be acting upwards. Alright, so next for resultant of coplanar forces, we have resultant of two coplanar concurrent forces. So we have here two forces. We have F1 that is 350 newtons acting at an angle of 40 degrees, and we have F2 that is 200 newtons acting along the x-axis. So we're going to solve for the resultant of these two forces. What we will be using first is the analytical method. Okay, so for the analytical method, first we will be solving for the components of our resultant. So we'll solve for the x component and then the y component. Right, so for the x component or the horizontal component of our resultants, this would be basically the summation of all the forces along the x-axis or all the horizontal forces. And then for the vertical component of our resultant or Ry, it is just basically going to be the summation of all vertical forces or all the forces along the y-axis. And then if we want to solve for the resultant, since this is just basically a right triangle, we'll be using the Pythagorean theorem. So our resultant R is going to be equal to square root of Rx squared plus Ry squared. And then if we want to solve for angle theta right here, we will be using tangent. So to solve for angle theta, it will be just tangent theta is equal to Ry over Rx, right? So that's basically what we will be using for the analytical method. So let's start first with the horizontal component Rx. So it is going to be equal to the summation of all the forces along the x-axis. Right? So you might mistake this that this is going to be equal to 0. So our summation of forces is only equal to 0 when we are talking about equilibrium of our forces. Our topic is resultants. So this is not going to be equal to 0. Okay, so first off, let's start with F2 since this is a horizontal force. So we have 200, and then the horizontal component of F1. So for the horizontal component of F1, right here, this is going to be F1 or 350 cosine phi or 40. Alright? So solving this, we have Rx that is equal to 468.12 newtons. That is acting to the right. Alright? Next, for the vertical component or Ry, so this is just going to be the summation of our forces vertical. So for F2, we don't have any vertical components for this one, but our F1 has a vertical component. Solve for the vertical component of our F1, this is just going to be 350 sine 40 degrees. And our Ry now is equal to 224.98 newtons. That is acting upwards. Alright. Now we have our components, our Rx and our Ry. We can now solve for the resultant. So our resultant R, this is going to be the square root of Rx squared plus Ry squared. So this is going to be 468.12 squared plus 224.98 squared. And that is going to be equal to 519.37 newtons. Next, to solve for angle theta, our angle theta is just going to be equal to, or rather, tangent theta is equal to our Ry over Rx, which is our Ry is 224.98 divided by 468.12. Now you could solve this in your calculators by using shift solve, or we could further simplify this. Our angle theta would be equal to arctangent 224.98 divided by 468.12, and that is going to be equal to 25.67 degrees. All right, so that's our solution. So this is going to be our resultant, and this is going to be its angle. So although we have shortcut methods or calculator techniques in solving for the resultant, so it's important to know the fundamental solution for this kind of problem using the analytic method. Because, for example, what if we don't know one of the forces, we don't know F1 or F2, but the resultant was given, and we are going to solve for the unknown force, so we can't use our calculator techniques to solve for that one. So we need to use this analytical method or our fundamental solution in solving for our resultant forces. Now, there's another way of solving this problem, and that is by applying the parallelogram law. Alright, so we'll be solving the same problem, but only this time we will be using the parallelogram law to solve for the resultant. So what is the parallelogram law, and how are we going to use that to solve for the resultant? So if we have two concurrent forces, the resultant of that is going to be the diagonal of the parallelogram that will be formed by those two forces. Okay? So basically, we're just going to be drawing a parallelogram. Okay, so to draw the parallelogram, we're just going to transfer or copy our first force or F1 on the tip of our F2. So we're going to draw it this way. Okay, so wait lang. So for our F1, and then for our F2, we're just going to be drawing it from the tip of our F1 towards here. Alright, so this is going to be our F1, or rather our F2. So this has the same magnitude and the same direction as your F2, and this one has the same magnitude and direction of F1. Right? And to solve for the resultant, our resultant is just, as I stated earlier, this is just going to be the diagonal of our parallelogram. Okay? So, maybe we should isolate this triangle, but first let's identify some angles first. So if this is 40 degrees, this one should also be 40 degrees, right? So let's write down our angle. So this one is also going to be 40 degrees. And if this one is 40 degrees, this one is going to be, so 180 minus 40, that's going to be 140 degrees. Right? So let's isolate that triangle. Alright, so we have our first triangle right here. So, to solve for the resultant and angle theta, or the direction of our resultant, we will be utilizing our sine and cosine law. So that's why the first video for this series was your application of trigonometric principles and concepts for engineering mechanics. Okay, so to solve for the resultant, we will be applying our cosine law. So for our resultant, it's going to be r squared is equal to F1 squared plus f2 squared minus 2 times f1 times f2 cosine 140 degrees, our included angle. Right, so let's substitute the values. So our f1 is 350. So that's squared plus f2, that is 200 squared minus 2 times 350 times 200 cosine 140 degrees. And that is going to be equal to 200,069,746.22. And for our r, so we're just going to square that. It would be equal to 519.37 newtons. Right? So we have our resultant. So let's write this is using cosine law. So next, to solve for the direction of our resultant, we're going to be using our sine law. So for sine law, we're going to be using our f1 over sine theta. And that should be equal to our resultant sine 140 degrees. Right? So we already know our resultant, and that is 519.37 newtons. And our f1 is given as 350. So the only unknown value here is going to be theta. So let's try and solve for theta. Right? So sine theta is just going to be 350 times sine 140 divided by 519.37. And let's isolate our theta. So this is going to be arc sine 350 sine 140 degrees divided by 519.37. Alright, so angle theta is going to be equal to 25.67 degrees. So this is the resultant. This is our direction. So it has the same result, just like on our first solution. Okay? Okay, so let's try and solve this one using our calculator techniques naman. So to solve this one, we need to use the complex mode. So just press mode and select 2. So we are now in complex mode. So first, let's look at our F2. So 200. So it has no angle. So angle 0 siya. Plus F1, that is 350. And it is acting on an angle of 40 degrees. Right? And then just press equal. And what you get here is the components of our resultant force. So you have your 468.11 or 12. That is going to be our horizontal component of the resultant, or Rx. And then we have here 224.98, and that is going to be Ry, or the vertical resultant of our, the vertical resultant. Okay, so if we want to solve for the resultant, which is what we're trying to solve in this problem, so what we're going to do is we're just going to convert this into a polar. So we're just going to click apps and then select 1 and then press equal sign. And there you go. You're going to see the resultant, 519.37, and the angle, which is 25.67 degrees. Right, so that's for our calculator techniques. Next, we have resultant of multiple coplanar concurrent forces. So as you can see here in our figure, we have four forces with different directions and different magnitudes. Now for the analytical solution, we're just going to sum up the all the horizontal components so that we could get to the horizontal component of the resultant. And we're going to sum up all the vertical components of our forces so that we could get the vertical component of our resultant, Ry. So solving for Rx, it is just summation of all the forces along the x-axis. So we're going to be considering the horizontal components of our forces, right? So let's start with F1, 35. So we're going to assume a positive direction acting towards the right side. Then for the summation of forces vertical or along the y-axis, we're going to assume a positive direction of upwards. Okay. So for this one, F1, we have a positive component. So that's 35 cosine 30 degrees. And then for F2, our horizontal component is negative because it's acting towards the right side. So we have negative 40 cosine 80 degrees. And then for F3, we have negative 60 cosine 50 degrees. And then for F4, we have positive 30 cosine 40 degrees. And then we take the summation of this, what we get is the horizontal component of our Rx, which is 7.779 newtons. So since this is positive, that means this is acting towards the right side. All right. Next, for our y component of our resultant, just sum up the vertical components of all the forces involved. So first, let's start with F1. So it's acting upward, so that's positive. So we have 35 sine 30 degrees. And then F2, so this is again acting upwards. So that's positive sine 80 degrees. So positive 40 sine 80 degrees. And then we have F3. So this one is acting downward, so that's negative sine 50 degrees. So we have here negative 60 sine 50 degrees. And then for F4, acting downwards again. So we have negative 30 sine 40 degrees. Let's add that up. You'd get your Ry. And your Ry is negative 8.354 newtons. So since this is negative, it means that it's acting downwards. Then solving for your resultant, you just get the square root of Rx squared plus Ry squared. And we get R that is equal to 11.415 newtons. And then if we want to determine the direction of our resultant, we can do that by just getting tangent or getting theta. So we could solve for theta using tangent. So tangent theta is equal to R y over R x, right? And our theta is equal to 47.04 degrees. Okay, so if we want to use our calculator techniques, you have already mastered your doing the manual computation, your analytical method. So for our calculator techniques, we will do this using your complex method again. So to get to complex method, just click mode and then select 2. Alright, so we're now in complex method. So to solve for the components of our resultant, our Rx and our Ry, we're just going to add up our forces. So our first force, F1, is 35 newtons and its angle of inclination is 30 newtons. Plus F2. So our F2 is 40 angle of inclination. So you have to be careful with this one. So we're going to measure their angle properly. So we're going to start on the positive x-axis and then measure their angles. So from here to here. So that's 180 minus 80, and this is equal to 100. So we're going to use 100 here. Yan. Plus our F3, 60 newtons, 60. And then for the angle of inclination, so we could memorize. We could measure it from the positive x-axis. So that's 180 plus 50. We have 230. So we're going to use 230 right here. Plus F4. So that's 30. And then the angle. So for the angle, we could use this angle. So if we're measuring clockwise in the clockwise direction, this is going to be negative, right? So we're just going to place that as negative 40. Alright? And then click equal. So what you get from this one is the components. So for Rx, we have 7.779. And then for Ry, we have 8, negative 8.354. Alright? And if we want to get the resultant, we're just going to convert this into its polar form. So we're just going to click apps and then click one and then equal sign. And what we get is the resultant, 11.415, and then its angle of inclination, that is negative 47.041. So you notice from our figure, we're measuring angle theta clockwise. That means it's negative. That's why what you can see in your calculators is negative. All right. Next problem. So we have here given forces P sub 1 and P sub 2. Now the magnitude of P sub 1 is given, which is 12 newtons, but the magnitude of P sub 2 is not given. Although their directions are also given. So per P sub 1, it is acting on a 65-degree angle from the horizontal or x-axis. And then for P2, it is acting on a 28 degrees from our horizontal. And then from the problem, it is also given that the resultant of the two forces is upward or acting along the y-axis. Now, we are to find the magnitude of the resultant, but also for the magnitude of our second force, for force P sub 2. Okay, so for this type of problem, the difference here is that we don't know one of the forces when computing for the resultant. So again, let's look at the analytical method first, which is much more practical in solving this type of problem compared to using your calculator technique. Okay? So we know that to solve for the resultant, or rather to solve for the components of your resultant, you're just going to sum up the forces along the x-axis and then the forces along the y-axis, and then we'd be able to solve for our resultants. But in this case, our resultant is just acting on the y-axis. That means we don't have any horizontal component for our resultant. So summation of forces along the x-axis would be equal to 0. So if we did that, so let's try the summation of forces along the x-axis. So first off, we have our first force, P sub 1. So the horizontal component of that force is going to be cosine, or rather 12 cosine 65 degrees. And then for our P2, the horizontal component is going to be negative, since we're assuming a positive direction going towards the right side. So it's going to be negative P2 cosine 28 degrees. And the whole thing must be equal to 0. So again, it is going to be equal to 0 because the resultant is acting along the y-axis. So there's no horizontal component. That's why it's equal to 0. So we have this equation. We have one unknown. So we'd be able to solve for P2, which is equal to 5.744 newtons. Alright, so we've already solved one of our unknowns. Next, let's do a summation of forces along the y-axis, or all the vertical forces. So for the vertical component of our P1, it's just going to be 12 sine 65 degrees. And for the vertical component of P2, it's just going to be P2 sine 28 degrees. So they are positive because we're assuming a positive direction of going up. Alright? So this whole thing is going to be equal to Ry. But since our resultant doesn't really have any horizontal components, our Ry is actually going to be equal to our resultant. Alright. So we could equate this whole equation to R. We have already solved for P2, which is 5.744. So we have one equation, one unknown. We'd be able to solve for R. Right? And our R is equal to 13.572 newtons. Okay, so we've already solved for the unknowns in this problem. So if you want to use your calculator techniques for this problem, we could use your stat mode and solve for the components of our forces. So let me bring up our calculator. Calculator. There you go. So for our calculator, if we want to use our stat mode, you go to mode and then click 3 for the stat mode and then just CA. And then for this one, if you want the components, you're going to select rectangular coordinates. So click shift and then rec, the minus sign. And then just input the coordinates. So for P1, or rather for P2, since this is unknown, so we could just type in 1 there. As you can see in this figure. So let's type in 1 and then the angle of inclination, shift, comma. For the angle of inclination, we're going to use the standard measure. So coming from the positive side of your x-axis, measuring towards the line of action of our P2. So this is going to be 180 minus 28 degrees. So let's just type in 180 minus 28 degrees. And then click equal sign. And then what you'd get here is well, um, the cosine. This one is going to be your cosine 28 degrees. And this is going to be your sine 28 degrees as well. So this is equal to cosine 28 degrees. This is going to be equal to sine 28 degrees as well. And then you just multiply this by P1, multiply this by P1, you'd get the components. Oops, sorry, you're not actually seeing the... Let me move our calculator first. There you go. So what we actually was what we were able to solve is the components times or rather the horizontal and vertical components times P1. And then if we want to solve for the components of our P2, we just input its coordinates. So shift rec, and then for P2 it is 12 newtons. Shift, comma, and its direction, so it's 65 degrees, positive 65 degrees, equal sign, and we get the vertical and horizontal components of our P sub 1. So for P sub 1, this is going to be the x component and this is going to be the y component. All right? And we're going to use these components to solve for the components of our resultant. And since we know our Rx is equals to 0, we could solve for P2 from this equation. And then from this equation, we could solve for the resultant. Using the calculator technique for this problem would usually take more time than is necessary if we used our analytic method. So sometimes it's more appropriate to use your analytic method. In your review, what I would suggest is you don't really need to focus on the shortcut methods. The shortcut methods would come to you as you practice solving your problems. So it's better to solve different kind of problems to practice solving. And as you go along, you develop your own shortcut techniques and you'd know when you would actually need to use your shortcut techniques or your calculator techniques. All right? So let's go to our next problem. So here it is required that the resultant of the given force as shown is to be upward to the right at an angle of 10 degrees with the horizontal, and then we are to compute the value of angle alpha and also the magnitude of the resultant force. So what was given in the problem actually is your P1 and then your P2. Also, given not the magnitude of your resultant but rather its direction. So it is acting on a 10-degree angle with the horizontal. So what we're asked here is to compute for the magnitude of our resultant, but also for angle alpha. This is going to be our angle alpha. So angle alpha is going to be the direction of angle, the direction of force P2 with the horizontal line X. All right. So let's explore the different ways on how we could solve this problem. So let's recap the problem. So what was given? So we know P1. So P1 was given. So it is 200 kilonewtons. It is acting on a direction of 60 degrees from our horizontal. The magnitude of your P2 is given. It is 300 kilonewtons. But the angle of its inclination is not given. It is unknown, alpha, from our horizontal line. Um, the magnitude of your resultant is not given, but its angle of inclination is 10 degrees from our horizontal. So those are given from the problem. So focusing on those given, we can do our analytic method. So again, we're just going to sum up our horizontal forces so we could get the horizontal component of your resultant, and then sum up the vertical forces so that we could get the vertical component of your resultant. All right, so let's try that. So for the summation of forces along the x-axis are all the horizontal forces. First, let's consider the resultant. So the horizontal component of our resultant is going to be r cosine 10 degrees. And then that would be equal to the horizontal component of our P1, which is this one. So this is going to be 200 kilonewtons times cosine 60 degrees. So we actually lack 1 0 there. All right. And then for our P2, so for the horizontal component of our P2, it would be 300 kilonewtons times cosine theta, or rather times cosine alpha. All right. So let's simplify this. So we get 0.985 times r is equal to 100 plus 300 cosine alpha. Okay. So this is going to be technically the first equation, but we could further simplify this. What I did is I just divided the whole equation by 0.985 so that I could bring out our resultant R. Okay? Next, we have summation of forces along the y-axis are all the vertical forces. So let's start with the vertical component of your resultant. So this is going to be r sine 10 degrees. And that is going to be equal to the vertical component of P1, which is 200 sine 60 degrees minus, rather, minus the vertical component of our P2, that is 30 sine alpha. Simplify this, we have 0.174R is equal to 173.21 minus 300 sine alpha. Excuse me. So this is going to be our second um, equation. So again, there are different ways on how you could solve this. But what we're going to do is just we're going to substitute R, the equation for R, in this equation. So if we did that, just like written here, we have one equation, one unknown, we'd be able to solve for angle alpha. And angle alpha is going to be 20.7 degrees. And once we get angle alpha, we could substitute angle alpha in our equation 1 so that we could solve for our resultant force. Then our resultant force is going to be 386.4 kilonewtons. Okay, so let's explore another way of solving this problem. So if we apply the parallelogram law to these two forces, or P1 and P2, the diagonal of the parallelogram that we could make from these two forces is going to be equal to our resultant, right? And if we take the triangle from this parallelogram, we could apply our cosine and our sine law. Now, remember that for cosine law, you need at least two sides and the included angle. And then for sine law, you need at least one side and the angle opposite that side. All right. So in our case, if we examine the properties of our triangle, what we'd be able to apply is the sine law. Right. So from the given, this side of our triangle is going to be equal to our P1, which is 200 kilonewton. And the angle opposite our P1, we're going to name that as our angle phi. All right. And then for our resultant force, the angle opposite that, we're going to name that as our angle beta. All right. So from the given, we know that our P1 is acting 60 degrees from the horizontal, and our resultant force is acting 10 degrees from the horizontal. Therefore, we know that this angle is going to be 50 degrees, and this angle is also going to be 50 degrees. So we have two parallel lines bisected by a straight line. The angles inside those lines must be equal to each other. That's why this angle is going to be equal to each other. So we have 50 here and then 50 here. Okay, so we have 50 degrees there. The next thing that we know is that our angle phi is actually going to be equal to 10 degrees plus our angle alpha. All right. So first, so we have one side that is 300 kilonewtons, and then the angle opposite that side is going to be 50 degrees. All right. So another known side is this side, and that is equal to 200 kilonewtons. But we don't know angle phi. So to solve for angle phi, we're just going to apply our sine law. So we have here 200 is to sine phi as or equal to 300 all over sine 50 degrees. So we have this equation, one unknown, we could solve for angle phi. And that is going to be equal to 30.71 degrees. And then from that, we'd be able to solve for angle alpha. So we know angle alpha is just equal to phi minus 10 degrees. And that is equal to 20.71 degrees. It's the same thing as that we have solved earlier. Okay. The next thing that we will be able to solve is angle beta. And we need angle beta so that we could solve for the resultant force. So angle beta is just going to be equal to 180 degrees minus 50 minus 30.71. So that came from the principle of our triangle that when you add all the angles, all the interior angles, it must be equal to 180 degrees. So we have 180 minus 50 minus 30.71. That is going to be equal to 99.29 degrees. And once we know angle beta, we can now solve for our resultant force. So our resultant force all over sine the opposite angle, 99.29 degrees, is equal to 300 sine 50 degrees. So we have this equation, one unknown. We can now solve for our resultant, which is 386.486 kilonewtons. And it's the same one that we have solved earlier. All right. So let's uh let's check another method where we could solve this one. A bit much more simpler, I guess. So I think the next thing that we could do is we could rotate the x and y axis. So the x and y axis, the main principle that you should always remember is that this is 90 degrees from each other. So they are perpendicular to each other. So if you're going to rotate this axis or these two axes, you must maintain that principle. So for example, I'm going to rotate the x and y axis and make our r act along the x axis so that the vertical component or ry of our resultant force is going to be equal to 0. And you can see that here in our figure. So our resultant now is acting along the x-axis. So if we do the summation of our forces along the y-axis or the x-axis, we'd be able to solve for something instead of having two equations and trying to solve for those two unknowns in those two equations. All right. So for us to be able to solve for ry, which is for us to be able to solve for phi, your ry is now going to be equal to 0. And to solve for ry, it's just the summation of your vertical forces or the summation of all the forces along the y-axis. Right? So let's sum up the vertical forces. So the first one we have our P1. So our P1, this one, is going to be equal to 200 sine 50 degrees. So that's acting upwards. So that's positive. So our assumed positive direction is going to be acting upwards, huh? And then for P2, this one is acting downwards. So that's going to be negative. And that is going to be equal to 300 sine phi. And the whole thing must be equal to 0. So we have one equation, one unknown, we'd be able to solve for phi. And phi is going to be equal to 30 degrees 0.71, or rather 30.71 degrees. And from the problem, we are asked to solve for angle alpha. Angle alpha is just equal to your phi minus 10 degrees. So we have here phi minus 10 degrees, and that is equal to 20.71 degrees. That is for angle alpha. All right. Next, for us to be able to solve for our resultant, it is just going to be equal to our Rx. So if we sum up the forces along the x-axis or all the horizontal forces, we'd be able to solve for Rx, which is equal to your resultant force. And that is just equal to, first, the horizontal component of our P1, which is acting towards the right side. So positive tayo if it's acting towards the right side. So we have 200 kilonewtons cosine 50 degrees. And then for the horizontal component of our P2, again, it is acting towards the right side, so it's going to be positive. So it's equal to 300 cosine 30.71 degrees. So we have this equation. So we'll be able to solve for our resultant. And our resultant is going to be equal to 386.486 kilonewtons, just like what we have solved in the earlier methods. Alright, so that's it for the resultant of our coplanar forces. So we'll proceed with our next topic. So for our next topic, we have moment of force. So when a force is applied to a body it will produce a tendency for the body to rotate about a point that is not on the line of action of that force. So this tendency to rotate is sometimes called a torque, but most of the time in physics, it is just referred to as your moment of force or simply just your moment. Now, the magnitude of that moment is equal to the force that is being applied multiplied by the moment arm or the perpendicular distance d from the axis at point O to the line of action of our force. So this is going to be our t. All right. So as an example, solving for our moments. So first example, we have here an applied force F equal to 10 newtons. So if we try to compute for the moment at point O that is caused by this force, so to solve for that, it is just going to be F times D, right? And then for the sign convention, we're going to assume a positive moment when it causes a counterclockwise rotation, and a negative moment, or rather a negative moment when it is rotating on a clockwise motion. All right. So for our first example, our force F is causing a moment m sub O at point O, and that is equal to, so this is supposed to be negative. So this is going to be negative. Since this causes a clockwise rotation, that is negative 10 times 3. So that is equal to negative 30 Newton meter. So actually this is equal to your basic unit of work, or a joule. So a joule is a unit of work or energy equal to the work done by a force of 1 Newton acting through a distance of 1 meter. Alright? So another example. So what is the moment that is caused by our force F at moment or at point O? So if we look at this force, if we rotate this force at point O, it will cause a counterclockwise rotation. So our moment is going to be positive. So again, our moment m sub O is equal to, so this is supposed to be positive one. So this is going to be positive since this is counterclockwise. So the force F, 10 newtons, multiplied by the perpendicular distance or the moment arm, and that is equal to 2 meters. So as the name suggests, the moment arm or the perpendicular distance, this is perpendicular to the force up to the axis where we are considering our rotation. In our case, we're considering the axis perpendicular to point O. Alright? So, our moment O is equal to 10 times 2 or 20 Newton meter. So, what if we're considering a 3D force system? So, we have here force F again, which is 10 newtons. And we want to know the moment along the z-axis. Now, for the sign convention, when you have your 3D moments, so the positive direction or the sign convention for 3D force systems with regards to your moments is guided by the right hand rule. So, according to this rule, the natural curl of your fingers of the right hand, as they are drawn right here, so will present the positive direction of the rotation. Alright, as an example here, we have force F being applied at a perpendicular distance d from our point O. Now, if we want to measure the rotation at that point or our m sub O, so it is going to be, for the positive direction, it needs to be in this direction, as suggested by how your fingers would curl. Alright? So in this direction, if you point your thumb towards Z, the positive direction of the rotation is going to be this manner. So this should be negative. All right. So solving, if we want to solve for moment along the z-axis, we're just going to multiply the perpendicular distance, d, which is 4 meters, times the force, which is 10 newtons. So we have here negative 10 times 4, or negative 40 newtons meter. All right. So just as a reminder, this signs, be it your negative moment or positive moments, just indicates the direction of a rotation. All right. So next example. So we have here a problem. So we're going to find the moment of a force about point D. So this is going to be our point D, and this is going to be our force. So we have P that is equal to 500 kilonewtons. Now, for us to be able to solve this the standard way, we need to find this distance, this perpendicular distance to the line of action of our force, right? But this could be a bit difficult to do. So another easier way of doing this is by solving the components of our force P. So we'd have Px right here, and then Py here, and then solve for the moments. So we're just going to rotate your Py about point D, and then we're going to rotate Px about point D. So that's an easier way on how to do, less mistakes, right? So if we try this one, so let's solve for the components. So to solve for the components, the first thing that we need is this angle, or angle theta. And to solve for angle theta, we could consider this triangle. So this triangle has sides 8 meters, and this one is equal to 6 meters. And we're trying to solve for theta, so we could use our tangent. So TOA, opposite over adjacent. So tangent theta is equal to 6 over 8. Solving for theta, we'd get 36.87 degrees. Now, since we have our theta, we can now solve for the um, horizontal and vertical components of our P. So for Px, or the horizontal component, it is just equal to 500 times cosine 36.87 degrees, and that is equal to 400 newtons. Now for the vertical component, or Py, it is equal to 500 sine 36 degrees 0.87, or 36.87 degrees, and that is equal to 300 newtons. Alright, so since we have the components, so let's first rotate our Px to our point D. So it's going to rotate in this manner. So we'd have a counterclockwise rotation, right? So let's write this one first. So let's see. We're trying to solve for the moment at point D caused by our force. So we're going to consider our px first. So yeah, this one is going to rotate on a counterclockwise manner. So that's going to be positive. So we have positive px, that's 400. What is going to be our perpendicular distance? So this is going to be our perpendicular distance. So this is 9 meters. So we're going to multiply this by 9 meters. Alright, next we have our py. So for py, it is going to rotate on a clockwise direction. So this is going to be positive. So we are going to add plus py, which is 300 newtons. And then the perpendicular distance is going to be this distance, and that is 8 meters. So we're going to multiply this by 8 meters. All right? And the whole thing is going to be equal to, so we have 1,200 Newton meter. All right. So another way to solve this is by using this principle, the principle of your transmissibility. So the principle of transmissibility states that the point of application of a force can be moved anywhere along its line of action without causing or without changing the external reaction forces on a rigid body. So the line of action of our force P is going to be this one. So we could transfer our force P at any point along this line. All right? So as an example, let's say we want to move our force P at point C. So what we're going to do is, since it's quite difficult we don't want to solve for this perpendicular distance, we're just going to use the components Px and then our Py. So let's solve for if we move, for example, if we move our force P here, what is going to be our uh, moment at D? So let's write that down. So moment at D. So again, let's start with our px. So it's going to rotate again on a counterclockwise motion. So that's going to be positive. For the perpendicular arm, so this is going to be our perpendicular arm, which is equal to 6 meters. So we're going to multiply this by 6 meters. And then our py is going to rotate on a clockwise direction. Oops, sorry. This should be negative. This one should be negative, right? So again, this one is going to rotate on a clockwise direction. That means it's going to be, sorry, this is going to be negative. So we're going to subtract this one. And our py is 500. So for the perpendicular distance, we have this distance, which is equal to 4 meters. So we're just going to multiply this by 4 meters. Alright, so correction, this is supposed to be 300 newtons. So let's change this. Ah, kilonewtons. So this is supposed to be in kilonewtons. Alright. And 400 times 6 minus 300 times 4 would get the same value of 1,200 kilonewton meter. So what if we try to transfer again our force P at point D, which acts vertically along point D. So they are along the same vertical axis. So let's say we transfer it here. So again, let's solve for our moment. So at point D, wait lang. So at point D, our moment is going to be, first let's consider our px. So again, it's going to rotate on a counterclockwise rotation. And our perpendicular distance is going to be, this is going to be 3 meters. So we have positive 400 times 3 meters. And since our py is going to be concurrent with point D, so we don't have to consider that for the computation of the moment about point D. Alright, so we only need to consider 400 times 3, which is again equal to 1,200 kilonewtons per meter. So again, this is positive because it is rotating on a counterclockwise rotation. So that is just our assumed positive direction for this problem. So if you encounter this problem, it is much easier to have some of the components of your force be concurrent with your point of interest, just like in our problem. So this is just an easier solution for that one. So as a final note for this topic, so let's say you're interested in solving for distance D. And we already know the moment at D costs about force P, that is 500 kilonewtons. So as stated earlier, your moment at point D is just equal to your force times the perpendicular distance or the moment arm of our line of action to our axis or point D, right? So we know the moment, which is 1,200, and that is equals to the force, 500 kilonewton multiplied by D. And from this equation, we can now solve for D, which is just equal to 2.4 meters. All right. So let's proceed to our next topic. All right. So for our next topic, we have distributed loads. Our structures are designed to carry loads, and sometimes those loads are distributed over a surface area. All right. So the most common types of your distributed loads that you will encounter for your basic engineering mechanics and your structural theories are your uniformly distributed loads and your uniformly varying loads. Now, for a uniformly distributed loads, it means that the load is uniformly distributed or equally distributed throughout the, let's say this is a beam, throughout your beam or your structure. And a uniformly varying load means that for this one, the rate of decrease of your loading is the same throughout the surface area of your, let's say, beam or any type of structural element that you are trying to consider or trying to analyze, right? So, for us to solve the resultant of your, or the magnitude of the resultant of your, first, your uniformly distributed load, what you need to do is just compute for the area of your loading diagram. So something if it looks something like this, this is typically called your loading diagram. So for us to be able to solve for the resultant, let's just solve for its area. So let's say this uniformly distributed load has a 10 newton per meter magnitude. So to solve for your resultant, you just need to compute for the area. So let's say the length is 10 meters as well. So for its magnitude, we have 10 newton per meter times 10 meters. And that is equal to 100 newtons. And the location of that resultant is going to be on the centroid of our loading diagram. In our case, since your uniformly distributed load is your typically what is called your rectangular loading, so it occurs at the middle or at the midpoint of your total length. So in this case, since we're considering 10 meters, this is going to be 5 meters. 5 meters, right? So for your uniformly varying load, it's the same thing. You just need to compute for the area under your loading diagram so that you could compute for your resultant. In our case, your uniformly varying load typically takes the shape of your triangle, right? Triangle. So we have here your R is going to be one half base. Let's say again. So let's say this is 10 newton per meter, and this is going to be 6 meters. So one half base or rather height first, 10 newton per meter times 6 meters, and that is going to be equal to 30 newtons. And your resultant is going to act on the centroid of your triangle. In our case, this will be 1/3 from this side of your triangle. So 1/3 of your 6 is just going to be 2 meters. And this one is going to be 4 meters. All right. So next topic. So for our next topic, still on resultants of coplanar forces, but now we will be considering parallel coplanar forces. So these are forces that are parallel to each other but still on the same plane. So we are going to determine the magnitude and location of the resultant of the given forces. Now, solving for the resultant of your parallel forces is actually quite simple. What you need to do is you just need to sum them up together. In our case, since we have, now for the first example, we have two forces. One is a 20 Newton force, and then another one is a 30 Newton force acting on points A and B respectively. So we're just going to add them. So this is 20 newtons plus 30 newtons. That is equals to 50 newtons. So that is going to be our resultant. Now, for us to be able to solve for the location of our resultant, in our case, let's name that as your bar X. What we're going to do is we're going to apply your Varignon's theorem, or the principle of moments. So this states that the moment of a force about a certain point is equal to the sum of the moments of the components of the force about the point. So basically, what this says is that the moment at A due to R is equal to the moment at A due to your 20 Newton force and 30 Newton force. So that's basically it. So we're going to write an equation from this statement. So let's write our equation. So moment due to A, or moment at A due to R. So that is R times your bar X for your perpendicular arm or your moment arm. So let's assume a positive direction of counterclockwise for this one, just to keep in the practice of your sign conventions. So this is going to be negative since this will rotate on a clockwise manner. So that's going to be negative. The perpendicular arm, bar X. All right. So this is equal, according to your Varignon's theorem or principle of moments, equal to the moment at A due to our two forces. So we have 20 newtons and 30 newtons. But since your the line of action of your 20 Newton force coincides with your point A, we don't need to consider that for our moment. So that's going to be 0. And then we have your 30 Newton force. It's going to rotate again, clockwise direction. That means it's negative. The perpendicular arm is going to be 5 meters. So that's negative 30 times 5 meters. So we have already solved for your resultant force. This is going to be 50 newtons. And solving for your bar X, let's change the color. Solving for your bar X from this equation, this is going to be equal to 3 meters. Alright, so let's look at another example. Here we have three forces. 10 newtons, 25 newtons, and 15 newtons acting on points A, B, and C respectively. Now, the distance between point A and point B is 2 meters, and the distance between point B and point C is 4 meters. Solving for the resultant, again, we're just going to add them up. So this is basically just summation of vertical forces since our forces are all vertical forces. So this is just 10 plus 25 plus 15 newtons. And that is equal to 50 newtons. All right. Next, solving for our location of the resultant. So again, we're going to use your Varignon's theorem. So it doesn't really matter if point A is going to be your reference. So we could actually shift the reference point. So we could shift it to point B or shift it to point C. So in our case, let's use again point A. So the distance measured from point A, bar X for our resultant. So again, the moment at A due to R is going to be equal to moment at A due to 10 newtons, 25 newtons, and 15 newtons. Okay, so let's write the equation. So your moment arm is going to rotate on a clockwise direction. So that's negative. The perpendicular arm is going to be your bar x. So we have here negative r times bar x, and this is going to be equal to, so again, your 10 Newton force is acting, or the line of action of your 10 Newton force coincides with our point A, so we're not going to consider that. Next, we're going to consider your 25 Newton force, and again, it's going to rotate on a clockwise direction, and the perpendicular arm is going to be your 2 meter. So this is going to be negative. Wait. So we'll start with the 10 Newton force, that's 0, minus 25 newtons times 2. And then we have your 15 Newton force, again, rotating on a clockwise direction. So that's going to be negative. For the perpendicular arm, this is going to be 2 plus 4, which is equals to 6 meters. So that's negative 15 times 6 meters. All right. So you've already solved for your R. So again, this is 50 newtons. So we can now solve for your bar X. And your bar X is going to be 2.8 meters. All right. So that's how we solve for your resultants and the location of your resultants for your parallel coplanar forces. Next, let's consider the resultant of your non-parallel, non-concurrent, still coplanar forces. All right. So we have here 4 forces. First one is 70 newtons being applied vertically on our point, or at this point, and then we have 40 newtons acting at a 60-degree angle from the vertical, and then we have 60 newtons acting on a 70-degree from your horizontal rather, and then you have your 80 newtons here acting at 40 degrees from your horizontal. So we're going to solve for the resultant first. So for the analytical method, we're just going to sum up the forces, vertical and horizontal, for the components of your resultant. So let's say for the summation of forces along the x-axis, this is going to be equal to your horizontal component of your resultant. So if we start at your first force, so there is no horizontal component for this one. But the next force, the 40 Newton force, is going to have a resultant component. So again, we're going to assume a positive direction of going towards the right side. So this one is going to have a negative sign since it is acting towards the left side. So we have here negative 40 cosine 60 degrees. So we have here negative 40 cosine 60 degrees. And then for the next force, we have here 60 positive since it's acting towards the right side. Positive 60 newtons cosine 70 degrees. So we have positive 60 cosine 70 degrees. And then the next one, we have 80 newtons. So again, it's positive since it's acting towards the right side. So this is positive 80 newtons cosine 40 degrees. And the whole thing is going to be equal to 61.805 newtons. All right. Now for our RY. So we're going to assume a positive direction of going up. So this is going to be summation of all your forces along the y-axis, or all your vertical forces. And this is going to be equal to the vertical component of your resultant. So first we have 70 newtons acting downwards. So that's going to be negative 70. Then next we have the vertical component of your 40 newtons acting downwards. So again, that's going to be negative 40 sine 60 degrees. And then next we have your 60 newton, the vertical component of your 60 newton acting upwards. So that's going to be positive 60 sine 70 degrees. And then for the vertical component of your 80 newtons, it's going to be negative sine 40 degrees. So we have here negative 80 sine 40 degrees. So this is going to be equal to our vertical component of the resultant, and it has a negative sign and a magnitude of 99.682 newtons. So solving for the resultant, our resultant is just going to be equal to the square root of Rx squared, or 61.805 newtons, plus Ry squared, which is negative 99.682. So our resultant will be equal to 117.288 newtons. And then for the direction of our resultant, it's going to be tangent, wait lang, tangent theta. So our resultant, our Rx is positive. That means it's going towards the right side. And our Ry is negative. It means that it's acting downwards. So our resultant, so let's first, this is Rx, Ry. So our resultant will be acting on this direction. And we're trying to solve for our theta. Okay, so our theta is going to be equal to tangent theta Ry, or rather, Ry is 99.682 divided by Rx, which is 61805. Therefore, our theta is going to be equal to 58.2 degrees. All right, so we know the resultant. We know its angle of inclination. The next thing that we need to know is the location of your resultant. So for the location of our resultant, so let's apply our resultant in our figure just for the visual. So it's going to be somewhere, let's say here. This is going to be our resultant R. And let's say for the components, so this is Ry, this is going to be Rx, and this is going to be your angle theta. And then what we're trying to solve for here is going to be your bar x. So this is going to be your bar x. All right. So to solve for bar x, again, we're going to be applying your variance theorem. That means that the moment, let's use a reference axis, this reference axis or this reference point at point 0. So that means that the resultant, or rather the moment at 0 due to R is going to be equal to the moment due to all the forces. All right? So let's write it down. So first off, the horizontal component of your reaction, or rather, the horizontal component of your resultant is acting along the line of, or is acting along your point O. So we don't need to consider that. What we need to consider is your Ry, or the vertical resultant. And for the sign convention, since this is rotating on a clockwise direction, this is going to be negative. So we have here, let's write it down. So we have here negative Ry times bar x, and that should be equal to, so for our first force, we have 70 Newton rotating on a clockwise manner. So that's negative 70. For the perpendicular distance, this is 2 meters. So that's times 2 meters. Next, we have the vertical component. So all horizontal components we will not consider since their lines of action coincides with our point O. So we're going to consider the vertical component of your 40 newtons. This is rotating on a clockwise manner, so that's going to be negative 40 newtons sine 60 degrees. And then for the perpendicular distance, this is 5 meters. So times 5. And then next we have your 60 newtons or the vertical component of your 60 newtons rotating on a counterclockwise manner. So that's going to be positive. So we have here positive 60 sine 70 newtons or positive 60 newtons sine 70 degrees. For the perpendicular distance, this is 8 meters from your point of origin. So let's multiply that by 8. Then next, we have the vertical component of your 80 newtons rotating again on a clockwise manner. So that's going to be negative. So we have negative 80 sine 40 degrees. And then this is acting at 11 meters away from your origin. So this is going to be times 11. All right. So we know our Ry, which is equal to negative 99.682. All right. So solving for bar x, we could get, or rather, we don't need to write this negative in our equation since we already considered um this negative sign for the rotation. So solving for bar x, we have one equation, one unknown. Solving for bar x, we'd get 4.292 meters. All right. So that's for the location of our resultant. Okay, so you might be wondering about the calculator technique for this type of problem. So yes, we could still use our complex method in solving for our resultant and its inclination or direction of application. But for the location itself, we can't use those calculator techniques anymore. Okay, so if we're interested in using the complex method or for our calculator techniques, there's something that you need to make note of is that when you measure the angles, it should be measured from the tail of your forces. So um, the angles is now going to be coming from the tail ends of your forces. So we're going to have here, so from the horizontal, this is going to be negative 90 degrees. This one. So this one is going to be 60 degrees. Therefore, this is going to be 180 minus 60 degrees or negative 120 degrees. Right? And then this one, so we have this angle. So we could measure this. Let me just erase this. Sorry. Uh, Give me a moment. Right. So for 60 newtons, so we're going to be measuring at the right side of your forces. So this is going to be 70 degrees. 70 degrees. So that's going to be positive since we're measuring it on a counterclockwise direction. And then this one is going to be negative since we're measuring it on a clockwise direction. So this is going to be negative 40 degrees. Right? So when using the complex method, maybe we should write it down first. So first off, we have our 70 Newton. So let's write it down here. For complex method. So the first one is 70 newtons. So we have 70 angle. It's going to be negative 90. Plus, we have 40 newtons. And the angle is going to be negative 120. Plus 60 newtons. And the angle is going to be 70. Plus 80 newtons. And the angle is going to be 40 degrees. Alright, so let's try that out in our calculator. So first off, let's go to our complex mode. So go to mode or click mode and then select 2. And then for the first one, we have 70 and then angle negative 90 plus 40 angle negative 120 plus 60 angle 70 plus 80 angle negative 40. And what we get is the components of our resultants. So we have here 61.805 for your Rx and then 99.682 for your vertical component. And if we want to solve for the resultant itself and the angle of inclination, just click apps and then select one, then click equal sign. And what we get is um, the resultant itself, which is 117.288, and then its angle is going to be negative zero point 0.2. So it's negative because the way it's measured here is on a clockwise direction from your positive x-axis. All right. So once you get that, if you use your calculator techniques, once you get the resultant, its angle of inclination, the next thing that you're going to do is you're just going to apply your Brennan's theorem to solve for bar x. Alright, so that's it for this video. Thank you for watching. I hope to see you on the next one.